Today we're going to talk about another question addressing this claim here. This first part is a knowledge thing about what happens when it boils. Important you still remember that, but we're not going to test you on that in IA1. Calculating specific heat capacity, that comes from analysing the data. Right, you should remember this formula, Q equals MC delta T. You put some heat in, tells you how temperature changes, or temperature changes, how much heat went in. Right? So we can use this formula and look at our graph to try to work out the specific heat capacity of water. We'll rearrange it because we've got T versus time, but start with T versus Q. Our temperature will be 1 on MC times Q. Using a heat transfer rate, 1,000 joules per second, that tells us that Q equals 1,000 times delta T, little t, delta time. So our equation for temperature change is 1 over MC times Q, 1 over MC times 1,000. So the slope of our graph during the heating phase, temperature versus time, is 1,000 over MC. You can also measure that slope by looking at the graph. And if you look at the heating phase, we increase our temperature by close to 70 degrees in 150 seconds. Calculate the slope. 68 over 150. Given your calculator, you get 0.453 degrees per second. So 0.453 degrees per second is 1,000 over MC. Subbing in the value for M that we're given, which is 500.5 kilograms, rearranging to get C. We end up with our value for C that is 4,411.8 joules per Kelvin per kilogram, which is close-ish to the accepted value. I'm not too unhappy with that. You don't know the claims, what about evidence? We look at evidence. Right? The graph shows the linear relationship between change in temperature and time. Right? And as the heating rate is constant, it shows a linear relationship between change in temperature and heat put into the liquid, which is exactly what the claim says, so the claim is supported. I point out that it is incorrect until you near the boiling point. So a caveat on this linear relationship is that it doesn't apply once you reach the boiling point. Right, so we want to predict what would happen if we change the volume. Well, the slope of our graph, predict everything is drawn in there. Right, the slope of our graph depends inversely on the mass of water. So if you halve the mass of water, you should double the graph, double the slope, up to the boiling region. So essentially, temperature change is doubled. It's going up twice as steeply, and we're getting our double slope graph. Shown in red.